Hey, math friends. So our learning target today is how we can calculate theoretical probability. So yesterday we talked about experimental, what happened in the experiment. Today we're going to talk about what we think should happen. So very much the idea of 50-50 when we flip a head. We predict that 50% of the time we get heads, 50% of the time we get tails. When you flip a fair coin and it's a fair experiment, that's our prediction of what we think should happen. But sometimes when we actually start flipping the coins and we do the experiment, sometimes that doesn't happen at all. So mathematically speaking, the more times you do the experiment or repeat the trial, the more likely you'll get to what you think should happen. So that at that point, the experimental probability of what happened should be very close to what we think should have happened. Not always the case. So example one's going to look very similar to what we did on our last lesson, experimental. We still have the same formula of kind of what you desire or what you want. In this case, you can see that it's like baby blocks with alphabet on it over the total possible blocks. So same kind of setup, it's just a different sort of analogy as we dig into the lesson. So no experiment happening today. We're just kind of trying to predict what we think should happen mathematically. So what's the probability that we get a vowel? This is the same question we had yesterday. Well, we have 1, 2, 3, 4, 5, 6, 7 letters. And how many of those letters are vowels? So we would predict that we have vowel there, vowel there, vowel there. So we have 3 out of 7 vowels. So what's the theoretical probability of choosing a vowel? I'm simply going to use division as we divide down and get a decimal there. So we have 3 divided by 7 gives me 0.428. I guess I could round that to a 9. I think I'll round that to a 9 because the next digit's a 5. When we convert that then to a percentage, we're just going to move the decimal 2 places to the right, 1, 2, which gives us 42.9% of the time we predict that we will draw a vowel on the first draw. Like the one draw out, we have a 42.9% chance that it will be a vowel. Does that mean if we repeat the experiment over a course of time that that's going to happen? Not a guarantee, but that's what we predict using good mathematics. So very similar to the start of how we did experimental. So theoretical today, what we predict will happen. So let's take a look at this problem here. What is the theoretical probability of choosing the letter X? So no experiment happening, just what's the probability that we will draw out an X? We know based on this question that we have 7 letters. And if we take a look at how many X's occur, we see 1 X. So we have a 1 out of 7 chance that that occurs. So division then, we would divide down. And we end up with 1 divided by 7. Gives us 143 when I round that last digit in our calculator. And we're going to convert that to a percent. We've been talking about that's the same thing as out of 100. So we're simply going to just move the decimal 2 places to the right. So having said that, we have a 14.3% chance that we're going to draw the X out on the first draw. That's the chance that we have. Does that mean we're guaranteed to draw the X out? No, actually a pretty low chance of 14%. So that's probability. Cool. So let's take a look at this question here. Example 2. I'm jumping around a little bit so they're not in order. The theoretical probability that you randomly choose a green marble from a bag is 3 out of 8. So probability that we draw a green. So this will be a prediction question. We predict 3 greens out of 8 in a bag. That's what we predict. Or that's the I misspoke. That is what has occurred. That is what our prediction is. I'm sorry. Stumbling. I got distracted here. There are 40 marbles in the bag. So instead of 8 marbles in the bag, if we change it to 40 in the bag, what do we predict? Now you clearly could use cross products on this. But I also do see that we have a pattern of times 5 times 5. And as we navigate, since the learning target doesn't say we have to use cross products, I'm going to use an easier step of, therefore, we would say that we have 15 green marbles out of 40. So we predict out of 40, in the bag that we should get 15 green. That looks like a 6 almost, so 15 green. So using our good math statistic that we have a 3 out of 8 chance, we predict 15 out of 40. That's called theoretical probability. Sweet. All right, jumping around. I'm going to come back to that one. I'm going to come back to that one. And let's talk about this next idea of impossible versus certain. So we have these probabilities of things that occur. There are sometimes things that cannot occur. It's impossible. And then there are sometimes things that always occur. So an impossible event has a probability of okay, I guess it's not going to work. Has a probability of 1. Or, sorry, a probability of 0. Impossible event. Means it cannot happen. That means that it cannot happen. Impossible event. So, for example, if I have a spinner, and this is blue, and this is red, and I ask you, what is the probability that I get green when I spin the spinner? You should say 0%. You have a 0% chance of getting green on a spinner that only has blue and red. So we would say that is a 0% chance, also known as an impossible event. Awesome. What's the opposite of that? A certain event. The probability of 1 whole or 100%. They're equivalent. 1 whole or 100%. It means that it's going to happen. It will happen. So if I ask you a different sort of question here on this same spinner, and I ask you, what is the probability that I either will get blue or I will get red? What's the probability that I get blue or red? You would say, well, 100%. Because 100% of the times you're either going to get blue or red. Well, what happens if I land on the line? If you land on the line, you're going to respin. So you have a 100% chance that you get blue or red. That's called a certain event. That certainly will happen. So example, this one's a little bit tricky because I actually do have a couple 5th graders that attend my class. So you have to roll with this one a little bit. But what's the probability that all of my students go to Skyview? You got to bear with me on that for those of you that actually go to an elementary school in our district. You would say 100% chance. So if, let's say if I have 150 kids, we would say that 150 students out of 150 attend Skyview, which is 100%. Now, what is the probability that every single one of my students is 12 years old? If I asked you to raise your hand, we are in class right now, and I said, how many of you are 12? We would count, we'd survey. We had asked you how many are 13, we'd count, we'd survey. Maybe some of you are 11 or some of you are 10. So is it true that all of my students, every single one of my students is exactly 12 years old? No, not true. 0% chance that all of them are 12 years old. Not what percent are 12. I'm just asking what's the chance that every single kid is 12. Not possible. Some are 12, some are 13, some are 11, some are 14, and so on. So some other language being used there. So let's take a look at this scenario. Each letter of the alphabet, just note that the alphabet has 26 letters, in case you forgot, no big deal if you did, is printed on an index card. What is the theoretical probability of randomly choosing any letter except Z? So the probability of any letter except Z. So we'll say not Z. So I'll draw a line through it, not Z. So of the 26 letters, how many of the letters are not Z? Well, if we know the alphabet, right, and we know there's 26 letters, we know that 25 out of the 26 are not the letter Z. So to find the probability of that, we're going to divide down. So we have 25 divided by 26 gives us 96%. So we get 0.96, which is 96 hundredths. When we convert that to a percentage, then that becomes a 96% chance that if you grab out an index card out of a stack, the probability that you will grab a card that is not Z is 96% chance using theoretical probability. All right, so I'm going to jump around here and kind of pick what I want yet today. I'm going to pause the video for a minute and figure out what I want to cover yet. All right, on a game show, a contestant randomly chooses a chip from a bag that contains numbers and strikes. So you have this bag that some of them have numbers and then some of them have like a strike. That means like you lost. The theoretical probability of choosing a strike, that stands for strike, is 3 out of 10 chance. That of the 10, 3 of them would be strikes. You're going to use prediction here, so we're going to do cross products. There are 30 chips in the bag. Our prediction is how many do we predict are strikes. So instead of having 10 in the bag, what happens if we have 30 in the bag? How many of them are strikes? So you could take cross products. I see a nice, beautiful pattern here. Nice, lovely pattern. We're going to say 9 strikes out of 30 is what we predict. We predict 9 out of 30 strikes in the bag, which means 21 of the letters, 21 that are in the bag are numbers. 21 numbers, 9 strikes. There's our 30. So that's a prediction question. All right, I need to cover one more experimental probability. I might not ask the question to its entirety. Let's talk about when a game is fair. When is an experiment fair? An experiment is fair if all the possible outcomes are equally likely. So if I ask you, what is the probability that player number 1 wins here in this experiment, in this spinner, what's the theoretical probability that player 1 wins? You would say, well, there are 4 sections, and 2 of the 4 sections represent player 1. So if we divide down, probably super obvious math here, we get 0.50. So we would say that player 1 has a 50%, I should not have used blue because we're talking about player 1, but player 1 has a 50% chance of winning, which means if player 1 has a 50% chance of winning, player 2 has a 50% chance of winning. So we would say that this game is definitely fair. That's a fair spinner. Fair spinner. So what would be something that is not fair? It would be this example. We would ask, does somebody have a better chance of winning than the others? Does somebody occupy more space of the game board, the spinner? And you would say, well, clearly player 1 has the best chance to win, a better chance than players 2 and 3. So this one would be not a fair spinner. It would be unfair to use that for any sort of real competition. That's just not fair. Everybody would want to be player 1. Okay. And last slide of the day, most likely. All right. Let's do this one. A number cube or a dice, they call it a number cube sometimes, but a dice is rolled. Determine if the game is fair. If it is not fair, who has the greater probability of winning? Okay. So you win. The probability that you win if your number is odd. So if we think of a dice, 1, 2, 3, 4, 5, and 6 are the numbers on a dice. We would say that you win if you get an odd number, 1, 3, or 5. So you win at 1, 3, and 5. We have 6 numbers on the dice over here. 3 of them are odd, 1, 3, and 5. That gives you a 50% chance of winning. So you have a 50% chance of winning. Awesome. Your friend wins if the number is even. So what's the probability that your friend wins? Well, your friend wins at 2, 4, and 6. So the probability that your friend wins is 2, 4, and 6, which is 3 out of 6. 3 of them out of 6, which is 50%. So would we say, first of all, determine if the game is fair, and we say yes, that game is fair. It says if it's not fair, then determine who has a greater chance of winning. We deem this as a fair game. You have an equally likely chance to win. You and your friend have the same chance of winning. You win with odds. Your friend wins with evens. Fair game. Question 10 is our last question of the day. You win if the number is less than 7. So the probability that you win, I meant to say less than 3. I don't know where I got the 7. You win if the number is less than 3, which means just the numbers 1 and 2. It says less than 3. It does not say equal to. So if you look at our numbers 1, 2, 3, 4, 5, and 6, of the 6, you win, you win. You have a 2 out of 6 chance that you win. I'm going to divide that down, which gives me 0.33. It's a repeating decimal, which turns into 33% chance that you win. We want to know, is it fair? Is it fair compared to your friend's probabilities? Okay, let's take a look at the last problem, last situation of the day. Your friend, got a lot going on my screen here, but if it is not less than 3, your friend wins. So what's the probability that your friend wins? It just cannot be less than 3. So it could be equal to 3, just not less. So 1, 2, 3, 4. All of these numbers are, we would say, are not less than 3. So your friend has a 4 out of 6 chance of winning, which is a repeating decimal of 66%. So I'm going to round that. So 67% when rounding. Is this a fair game? No. Your friend has a 4 out of 6 chance of winning. So who has a better chance of winning? Your friend. Why? 4 out of 6 is 67% chance of winning that game. So our summary for today's work is that we still are doing probabilities of events. We're still doing probabilities of events. If we get a fraction of something, let's say 1/4, we just convert that it's a 25% chance. Of course, that comes from the decimal 0.25. Also then, given that, if we know we have a 1 out of 4 chance of drawing a red out of a bag, we can use that to make a prediction of what should happen if we had 40 marbles in the bag. How many reds should we predict? So we can use our probabilities that are given to make predictions. That is our learning target for I can calculate theoretical probability. Have a glorious night.